want to start with? Anything that remind you where we were? We had talked about the Feynman propagator. Here we're just constructing it. We'll use it in the next set of lessons on interactions, but it's defined originally in terms of the time-ordered product of two fields, the xt phi of x prime t prime. And we did two things last time. One, we calculated it by knowing the solution's phi and just taking this expectation value directly. And we showed that it was integral d3 p over 2 pi cubed, 1 over 2 omega, theta of t minus t prime. So if t is bigger than t prime, it looks like e to the minus I p dot x minus x prime. And if theta is it's the complex conjugate of that. It's really the same thing. Sorry, let's be right there. Minus I x prime minus x. So basically it's symmetric in x and x prime, because by definition it is. Okay. And we also came up with a definition in terms of the four-dimensional Fourier transform. You know, d4p 2 pi cubed. Well, actually, let's use the notation q there. It's e to the minus I q dot x minus x prime over q squared minus m squared. So just a couple things to point out for what we're about to do. Omega here, omega is the square root of p squared plus m squared, where that guy is a vector p, okay? And just to remind you, all these things without vectors on it are four-dimensional dot products. So omega t minus t prime minus p vector dot x minus x prime vector. Okay, so remember to see through that. The other one that is important here is that q squared there is the four-dimensional one, so it's q0 squared minus q vector squared is q squared. Now it's not, and now q0, you know, colloquially is like omega, right? But here omega is p squared plus m squared. Here it's an integration variable, because here we integrate over all four components. There's an integral dq0 also. In that integration, and I see one typo, or printo, whatever, that should be a 4. Everyone see I slipped, I had written 3 there, I slipped it to 4 while you were looking at your notebooks. Okay. Okay. So these are somewhat different looking beasties. What we're going to do next is show they're equivalent, but the equivalence takes us into the magical world of I epsilon physics. Okay? And what I epsilon physics means is that this integral that's sitting at the top of the screen right now is ill-defined because it goes through a pole when q0 equals q vector squared plus m squared. Okay, you can see the pole about to pop out at you there. And how you treat that pole is essential for defining what that integral is. And the right answer, I'll stick it up above and then we'll write it down below also, is you put plus I epsilon there with epsilon equals a positive infinitesimal. Okay, so positive 0 plus means it's arbitrarily small but positive. Okay, and our task now is to prove it. Basically, what we're trying to do is we're trying to show that by putting this I epsilon there, we get that result out. Okay. So here's how we do this. Okay, so we add the I epsilon. The poles, in this case, get shifted slightly away from the real axis. We're integrating along the real axis, so we shift them slightly away, and depending on how you shift them, your integral has slightly different values. So here's where the poles are. The poles sit at q0 squared minus q vector squared minus m squared plus I epsilon equals 0, right? That's where the pole on that guy would be. Maybe I can have it sit there. Okay? That puts the pole at q0, well, it could be square root of q squared plus m squared minus I epsilon or it could be at q0 is minus this thing, q squared plus m squared plus I epsilon. Okay, so if you don't see that, you just basically it's q0 squared is q squared plus m squared minus I epsilon, taking it onto the other side. Now, one of the rules of I epsilon physics is that if you have a positive number times an infinitesimal, it's a positive infinitesimal also. So when I square this, I get this thing squared. The cross term is a positive infinitesimal times the minus I. And so I get this minus I. So you forget that there's anything out there. It's just a positive infinitesimal. And you drop anything with the infinitesimal squared. That's the rules of I epsilon physics. Okay? So does everyone see how this thing squared equals that? Again, any positive number times epsilon is just written as epsilon. It's just a positive infinitesimal, still infinitesimal. Okay? Comfortable with that? All right. So if we draw this on the q0 plane, here's the plane of q0. We used to have poles right on the real axis. Now we've shifted them. The one that's up, this is real q0. Here's imaginary q0. The one that's at positive values of real q0 sits down below the axis, and the one that sits at negative, that's dominantly negative, sits slightly above the real axis. So they're my two poles. Now they should be symmetric. Okay. So these guys, let me call it omega sub q. Okay, is defined to be square root of q squared plus m squared. Okay, so Q0 is integrated over omega Q is determined in terms of Q vector. It's not a separate integration variable. Okay, so it's clear now, if you've ever seen any of these constructions before, which most of you have, that the way to do this is you're going to do a contour integral. We're really integrating along this real axis, but we're going to want to do a contour integral. We're going to either close it in the upper half plane or the lower half plane. Okay. And we have to decide which it is. So we're to do contour integral, okay, well, what determines that? What determines that is you want the contour at infinity to vanish. You don't want it to be a big contribution. And in the integral that we have to do, we've got that exponent there. And we're doing the Q0 integral. So we want that to be exponentially damped. So let's just take a look at that. Let's look at it in more detail. We have e to the minus I Q0 t minus t prime. That's the Q0 part of the integral. That's e to the minus I real Q0 t minus t prime e to the imaginary part of Q0 t minus t prime. Okay, so if it picks up a real and imaginary part, the imaginary part goes like this. Okay, so if t is bigger than t prime, then t minus t prime is bigger than 0, then if you're going to close the contour with some imaginary Q0, you want imaginary Q0 to be less than 0 on the circle at infinity, because then you get e to the minus infinity, okay, on that circle. So you're closing it way out here at infinity. If the mq0 is less than 0, then you get. So this tells you that for this time, you close it in the lower half plane. Okay, that plane. Okay, so in other words, the contour goes out here, comes down, blah, 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 down like that, comes back around and comes back up. Then the integral along the line is the same as the integral around the whole contour. But if the reverse happens, t prime is bigger than t, so that t minus t prime, oh no, don't. Don't send. All right, send. Don't do something. This rarely happens, actually. Let's try Control Delete. Are we safe? Let me try. There we go. Good. Okay, good. I think we're saved. So t minus t prime is less than 0 in this case. So that means that to make that contour vanish, you want to choose mq0 is bigger than 0, so that again the exponent disappears at the circle of infinity. So then you close it in the upper half plane. Okay, so the two choices then we're going to do a contour integral. We're going to pick up the residue at the poles. The residue at the poles will be different in the two cases, but they'll be, that gives us the two different contributions. Okay. So the last thing we need to do then, before actually doing it, is when I write this 1 over q squared minus m squared plus I epsilon, that has the two pieces, the q0 minus omega q plus I epsilon, and 1 over q0 plus omega q minus I epsilon, if I have this right. Okay. So the then question is that the residue at the poles. Let me do one of them. I'll do this is the pole at for t bigger than t prime. The pole is at omega q minus I epsilon. Okay. Then the second part here goes into the residue. Okay, so I df is minus 2 pi I actually, I just, there's actually, I have an I missing up here. If I'm going to go back and put your I back there, that's, that actually, I forgot to stick it before. Okay, so let's do that. So the 2 pi I, here comes this I. So from closing the contour, we still have an integral d3q, 2 pi to the fourth. I haven't gotten rid of the 2 pi to the fourth, except that 2 pi will cancel it there. We're working on the piece that is true when t is bigger than t prime. And the residue is then the rest of the function with that pole removed. So this part of the residue right there becomes 1 over 2 omega q. Okay, at this stage you can drop any I epsilons because they're not needed anymore. And then I still have the exponent up here, e to the minus I e t minus t prime. Actually, that's omega q also. That's evaluated at q0 is omega q, and e to the plus I q vector dot x minus x prime. Okay, so in this case I pick up that piece. In the case of the other one, when I do it in the lower half plane, I get a minus sign because the contour runs the other direction. I get theta of t prime minus t. I get the residue. So now this guy is the pole, and this guy is the residue. And so q0 is negative. So this becomes minus 2 omega q. And then I get up here e to the minus I times minus omega q t minus t prime in e to the I. Hard to work on that little edge there. And then there's some brackets implied. Okay, so if I've done this, I get the i's end up canceling. The 2 pi's cancels one of them. It becomes the cubed. I end up with integral d3q over 2 pi cubed, 1 over 2 omega q in both cases, theta of t minus t prime, e to the minus I, q dot x minus x prime. Now all 4 vectors there, and there's a theta of t prime minus t, e to the plus I, q dot x minus x prime. And it's the 4 vectors also. Okay, which is the form I got before, or I started with. Okay. Sure. Okay, because I yes. So you're asking right there. That, yeah. Because what I was doing is I was doing the Q0 integral by a contour integral. So basically what I'm doing is I'm doing dq0 from minus infinity to infinity 1 over q0 squared minus this guy q vector squared minus m squared plus I epsilon. Okay, and that's then minus 2 pi I times the residue. Okay, actually, so here's what I did. Let me write out one whole step here. I turned this into then the contour integral dq0. In this case, I took it around the lower half plane, but the upper half plane is the other guy, the other case of, and I have this exponent here, e to the I q0, e to the I q0 t minus t prime over the same thing. Okay, so the first step I did is I took the q0 integral that's sitting right here, I turned it into a contour integral over a closed loop, and then I evaluated that using Cauchy's theorem as minus 2 pi I times the residue at the pole. In this case, the pole was at q0 equals omega q minus I epsilon. And the other case, there's the other one. Okay? So the contour integral is represented by the residue at the pole, and what I wrote out there was the residue at the pole. Okay? People comfortable with that? Okay? So this is a pretty standard trick. A place you've probably seen it before. Yes?
But you have two theta functions because you integrate over the entire?
No, okay, so this theta function is when if t were bigger than t prime, I close it in the lower half plane and I get this answer. Okay? In that case, this term 0. Okay? In the case that t prime is bigger, t minus t prime is less than 0, I do something different. I close it in the lower half plane, and so I don't get this guy anymore. I get that as the answer. I didn't work that one out in as much detail, but basically you get an extra minus sign because your contour is running the opposite way, and you get a second minus sign because your pole is sitting at negative omega. Okay, and they compensate, and so you get back to this guy. Okay, so now just let's try to see through the math a little bit here. The thing I want to remind you of is E and M. Okay, those of you who had E and M's from me saw something like this once before, because we do this in E and M also, and we calculate the Green's function radiation, which is also called the retarded Green's function. Okay, and the answer there was the same thing, almost. It was e to the minus I q dot x minus x prime. So if I'm using my relativistic notation, but we did q0 squared. No, we didn't do that. We did q0 plus I epsilon minus q vector squared. Okay, so m is going to 0, clearly, because the equation is the massless wave equation. That's not an issue. But we had that, we put the I epsilon right there. Okay, and when we did that, that's the poles down here. Okay, we closed it in the lower half plane, like that, and we get something. Okay, let's not bother writing out what the answer is. But you can see actually from the construction we did up above that if we have the poles down below, that corresponds only to t bigger than t prime only. Okay? So that's what we did in EM. What's different here? So the physics, we've got all these. That's the math. There's what a mathematician would tell you. What's going on here? Why do we do one in E and M and one here? So in E and M, remember, our problem is the following. We take some little source here. Here's some little charged particle. We oscillate it up and down. So here's a charge oscillating up and down. We then look out here at the radiation that's coming out. And we ask, what's the radiation? Okay, well, what we want then, this has happened at t prime, this is t, that's the way we set it up. We would then want t bigger than t prime only for causality. Okay, you wouldn't want the signal arriving with t prime less than t before it started wiggling. So you only want this one solution. Okay, so E and M, that's understandable. What happens in quantum field theory? Okay, where this is going to be used in quantum field theory is in interactions. Okay, we will use this propagator. Let me put one up, a Feynman diagram up here, just to get you thinking about it. You know, so imagine an electron coming in, scattering off a proton into some final state by exchanging a photon. That's one of the things that we'll do. This photon, in this case, would be described by a propagator, just one of these Feynman propagators. And the physics here is that this scattering has two components. We could imagine the electron coming in, t. Now, this diagram, this is a Feynman diagram. there's no time ordering associated. No time implied. Okay, so when we see the pictures and develop them, I can draw them. You know, I do sort of draw arrows to show you which way things are moving, but I'm not going to. But the location of that. This next thing, I'm actually drawing time-ordered pictures. So if I had, if one interaction happens at t and the other happens at t prime, it could happen that at t you emit a photon and it gets absorbed over on the second guy. Or you could have t prime and t, let's see, this is the proton is the bottom line. T prime govern the emission, and T govern the absorption. So these are time-ordered pictures. Okay, so that's not exactly the same thing as above. So, but the physics is that this Feynman picture with this Feynman propagator is going to contain these two diagrams, and those are the two theta functions that we found there. If t is bigger than t prime, you get one answer. T prime is bigger than t, you get the other answer. So the Feynman propagator contains both these, which are appropriate for an interaction, since you're not clear who emits first, who absorbs. So it's a different problem, and the placement of that I epsilon reflects that. Okay, so we've got that. This is also visible in perturbation theory. Okay, if you were doing perturbation theory, you're starting with some initial state, some interaction, some intermediate state. And here's second order perturbation theory. Ends up with some final state. So there's you sum over all possible. See if I can squeeze a summation sign in there. Okay. In some perturbation theory, you're supposed to sum over all possible intermediate states, and these are two intermediate states that you can have there. Okay, and it's remarkable that I'm not going to do it right now, but this expression and the expression that we get out of perturbation theory are essentially the same, and this factor here, this I, E minus EI, is essentially that propagator there. Okay? You know, when you go to continuum notation, the sum over I becomes the integral d3p. You're also instructed to sum over all possible energies. That's like that Q0 integral above. There's a pole in this integral also in that case. And to make this integral well-defined in perturbation theory, you'd have to put a little plus I epsilon there, the same I epsilon as we put above. Now this is too much to show at this moment. It's not appropriate to show, but that's nevertheless, the Feynman propagator is that sum over intermediate, equivalent to that sum over intermediate states. Okay, basically what we're going to end up doing is representing those two diagrams there by a single Feynman diagram and build up processes like that. All right, is that enough heavy-duty stuff for the moment? Yes.
What would change if you choose epsilon to be negative?
Well, your times, the way you should have done it if you choose epsilon to be negative is if you'd also, it'd be okay if I changed this sign right there to be a plus sign, and I can make epsilon negative. So there's a convention that goes along tying that minus I there with this sign on this. Okay, but if I kept this way, and I chose epsilon negative, or made it minus I epsilon here. And so it's actually a question. Keep that unchanged and do that. Then I would have reversed the time orderings in this, and so it would have been, these two would have been, this would have been interchanged over here. That's really all that would have happened. But when you get to doing the Feynman diagrams, you would have had both these causalities backwards. So you have blown causalities, basically. You would have had the emission event taking place after the absorption event. Okay, that's what would have happened. That's what it would have implied. The formulas would have implied that. So you would have lost causality. It's just like this was a form of causality. This I epsilon is a form of causality also. Okay. Okay, so heavy duty stuff, but once you get used to it, it's real easy. Okay. Last thing I have to do on this field is I've kept promising you some comments on the 0-point energy. Okay. Remember, when we had sum over various energy states, 1/2 h bar omega sub s, A of s, A dagger of s, plus A dagger of s, A of s, we turn that into sum over s h bar omega, A dagger A, plus the 0-point energy. That's the 0-point energy. Okay, so E0 is the sum over all states of 1/2 h bar omega sub s, and in the continuum notation, it's V integral d3p over 2 pi h bar cubed 1/2 h bar omega p. Okay, so this V came from the delta function of 0 that you get in the continuum notation. I don't know if you remember that. And, it's badly divergent. This guy, if you took statistical mechanics, remember, is the statistical mechanics counting factor. One state for every 2 pi h bar in phase space. That's how you count in statistical mechanics. So this is basically 1/2 h bar omega for every state. Okay, so it's okay. Of course, this thing is a formula goes to infinity, and so if that generally bothers people. So here's various possibilities. Okay, well, one possibility is it's not really finite. Really not infinite. Okay, so maybe, for example, if you think about the fields that we started off with, we say there's actually only n springs in that case. And so the h bar, 1/2 h bar omega is really the h bar omegas from each of those springs. And so in phonons, strings, or ... it's really not, it never was infinite, you know, so the formulas that we got out of that, it's just the 1/2 h bar ohms from all those n springs, and so that sum is just an artifact of the continuum approximation. And in reality, that's a small percentage of the total mass of a solid. You know, the 1/2 h bar omega of the springs in a solid is negligible. So if you're doing phonons or strings, that makes good sense. If you're doing fundamental particle physics, you know, that would mean there'd be some fundamental discreteness somewhere at some high energies, which is hypothetical, but possible. But it's certainly the real solution for solid condensed matter physics. You just don't worry about it. Okay, so discreteness could actually be the solution. There could be a cancellation. Okay, we'll see that bosons have E0 bigger than 0 and fermions E0 less than 0. And if you just happen to choose the numbers right, if you do supersymmetry, is a boson-fermion symmetry, the symmetry of bosons and fermions. In that case, E0 goes to 0. Okay, so that's, of course, supersymmetry is broken, but then E0 still can become finite. It's then not as big a problem. Those are the two things people mention the most. There's some folks that might argue that, you know, gravity might make it finite. You know, that's a really speculative one at the moment. But basically, the argument is something like, you know, if you have a big energy density developing, then that starts gravitating. There's a lot of gravitational potential energy associated with it. Eventually, it overwhelms it, and you wave your hands and say, "That's that." That's a speculative argument. And the fourth is for you to discover. It's certainly an interesting question to see how to do it. Okay. Some other comments that once it's finite, okay, once it's finite, it then becomes what we call the cosmological constant. Okay, so that's called lambda is the energy density of empty space. So, you know, what this is an energy density if we have no particles around. So none of these particles are floating around. So it's the energy of the ground state of the theory, the vacuum. In Einstein theory, gravity responds to all forms of energy, including the vacuum energy, and so that's it. And if present measurements, so if things like the CMB are equivalent to a cosmological constant, this then ends up having the value of roughly 10 to the minus 3 electron volts to the fourth. It's actually an energy density. That's to the fourth. So it's in some sense measured, and why it's so small is a big mystery, but we don't have anything to add to it here. It's just a background constant for us. That was comment number 2, and comment number 3 is to explain this Casimir effect. Okay. The Casimir effect is the calculation is the following: is you you take a big box like we've been doing and quantize the photon in that box. You take two plates in there, filling up that box. So these are conducting plates. And you compare that energy, you compare that to the situation where you don't have the conducting plates. So this is E0 is sum over all things 1/2 h bar omega with plates. So let me put P on it, minus sum over all states 1/2 h bar omega no plates. And you find that difference is not equal to 0. And you find what you find is that you can take the energy and convert it to a force by taking the distance derivative. The force per unit area is minus pi squared h bar c over 240 d to the fourth. And I think the h bar c is there. It's a little hard for me to know for sure, but I think I did the dimensional analysis on that right. Okay, so the Casimir effect, the force on these conducting plates can be calculated by a difference of two zero-point energies, and the change in zero-point energies. Okay. Questions about it? Yes. Why is, okay, so you're coming up here to the question is, why is the energy negative in the case of fermions? Yeah. Okay. We'll derive it later on. It's not immediately clear, but there is a hand-waving explanation. If you've heard this Dirac C business, okay, the hand-waving explanation is that you've filled up this Dirac sea of negative energy states. You fill them all the way down to minus infinity, and that's what your sum is over that. Okay, and if that's satisfying, I'm happy. It's not to me, but that's the hand-waving version. The real version will be probably on Thursday when we do fermions. All right. Other questions? I'm finishing the real scalar field there right now. So that's we're introducing these fields. Okay. So if there's no questions, I'm going to move on to what is the complex scalar field. Okay. Normally, when we do quantum mechanics, we have complex wave functions psi and psi star are different. So it's natural in many cases to use complex fields also here. And they brings in one thing that is different. Okay, so we're going to have phi and phi star not be exactly the same. Previously they were forced to be the same. And so what we're doing here is we're going to have 2 degrees of freedom. Associated with this guy. And we will make the argument about particles and antiparticles and charges coming up. So really, this gets used the most in conventional field theory when you are dealing with a particle that carries a charge, you know, like a pion, charged pion or something like that, is a good example of one. It can be an electric charge, or it could be, we'll see that the idea of charge generalizes. It's not just electric charges, but certainly electric charge is a good example. Okay. Okay, so I'll just write it out. So the Lagrangian is d mu phi star d mu phi minus some function which is always a function of phi star and phi. Okay, so for example, v of phi star and phi could be m squared phi star phi plus lambda phi star phi squared plus, it could be higher. Okay. Okay, the couple comments about this. So, okay, we could, so comment number one could be that we could make phi and phi star equivalent to two real fields. Okay. So if I took phi as 1 over the square root of 2, phi 1 plus I phi 2. And phi star, of course, is the same thing with a minus sign. So phi 1 and phi 2 are real. We would then write out this Lagrangian would be 1/2 d mu phi 1 d mu phi 1 plus d mu phi 2 d mu phi 2 minus, well, let me just write, I'll write the v. So it's the m squared over 2 phi 1 squared plus phi 2 squared minus lambda over 4 phi 1 squared plus phi 2 squared squared. Okay, so it's a particular form for two real fields. So if I just looked at this, let's just look at the phi 1s. The phi 1s would have been exactly the Lagrangian I wrote out for a real field. Likewise for the phi 2s, but they come in a particular combination. It's always, here are the interactions, phi 1 squared plus phi 2 squared quantity squared. Okay, one of the things you'll notice, it's not a big notice, but it's a signal of something, is that there's no factors of a half here and there are here. Okay? Now partially it's just come from this 1/2 there, partially it's convention, but when you write the complex scalar field you don't have factors of a half that you do with the real field. Okay, that's just, you'll see it works out that way. That's the way it works out. It's the right normalization. Again, these normalizations look like they're magic, but they've been chosen just by working out the answer and getting the result you want. John?
Is there a reason you don't have effectively a phi Q field other than it doesn't make numeric sense?
Yeah, so in this case, yes, there is a physics reason here. In fact, the physics reason is that in the case of the complex field, so it's easier to see probably up here, you can't write out a real Lagrangian. Lagrangian, the action is a real number. Okay? So the Hamiltonian Lagrangians all are real combinations of the field, and you can't write out one that has, you know, phi star phi is not real. Okay, the second way of answering that is that really this has a symmetry, which is phi goes to e to the minus I theta phi. So if I change the fields, phi star goes to e to the plus I theta phi star. If I change these things by a phase, then the whole Lagrangian is invariant. You can see phi stars phi is always up there. So there's this phase symmetry, which is mathematically, it's called a U1 symmetry. So if you see U1, that's all it means. It means that there's a they're invariant under a phase. Okay. Okay. The equations of motion okay, the equations of motion are derived. You treat phi and phi star as independent. Okay, so that's a little bit of a wrinkle here. Phi and phi star are there's 2 degrees of freedom. There's either phi 1 and phi 2, or phi and phi star. Okay, so let's just do that. Let's write out an equation of motion. The one I'll choose to do is I take the variation of the Lagrangian with respect to d mu phi star. I take d mu on that minus the variation of Lagrangian with respect to phi star equals 0. Or I could do it with respect to phi. Okay. Let's see if we can get it up there. There. No, I can't get it up there. But you can see the variation of the Lagrangian d mu phi star is d mu phi. Okay, right, so there's d mu phi star. Sorry, vary that. The variation of the Lagrangian with respect to phi star itself is, well, it's minus m squared phi minus, it's actually 2 lambda phi star phi phi. Okay, and so that variation comes from the V piece. Okay, so the equations of motion then turn into this first one here. That guy combined with that gives me box phi minus m squared phi minus m squared phi minus 2 lambda phi star phi phi equals 0. So that this thing starts off with the usual Klein-Gordon equation. Okay, this is that's and equals with a minus sign. Here's some interaction piece. Let's not focus on that. This is the part that's important. Is you just get the usual Klein-Gordon equation out. Okay, and likewise for phi star, you also get something the same. You get the Klein-Gordon equation on phi star. Okay, so there really isn't anything particularly different here. You know, I had some comments on the symmetry and stuff like that. There is a wrinkle in the quantization though, and that's where I want to spend a few moments. Okay, the solutions. So they satisfy the Klein-Gordon equation. Integral d3p 2 pi cubed 1 over square root of 2 omega p e to the minus I p dot x A of P. So that's the obvious thing here. Plus e to the plus I P dot x. And now, hold your breath, here comes the big surprise. The big surprise is I write B dagger of P. There, okay? All right. Previously I wrote A and A dagger, and I wrote A and I dagger because it was a real field, and so you had something plus its Hermitian conjugate. But now this isn't a real field anymore, so this guy isn't the Hermitian conjugate of that. Okay, so that's now something new. Okay, but just starting there, then everything else goes as before. I take pi of x is the derivative of the Lagrangian with respect to phi dot. Turns out to be d0 phi star. And the fact that there's a star there is interesting. Pi star of x is the derivative of the Lagrangian with respect to phi dot star. Pi star dot is d0 phi. Yeah, if I was doing that, so the Hamiltonian is pi phi dot minus plus pi star phi dot star minus the Lagrangian. You know, it's sum over all the different fields, p q dot. So that's how classical mechanics would tell me to solve this. And it turns out to be something pretty innocuous. It's d0 phi star, d0 phi, plus del phi star, del phi, plus m squared phi star phi. Plus, so, you know, there could be an interaction piece, but I'm just doing free fields here. Okay, so the nice feature about it is it's positive definite. This is, no matter what this is, that's positive definite. That's good news. So it's greater than 0. That's actually non-trivial. Okay. So that's still classical mechanics. Now if I want to do quantization, I want to do phi of x and t with pi of x prime and t. It's the same old deal. I delta 3 of x minus x prime. And you do the same thing with phi star with pi star, since they're independent fields. Okay, same thing. Okay, and now that enforces some commutation rules. And these things have been cleverly chosen such that this is satisfied if you take A of P with A dagger of P prime, it's 2 pi cubed delta 3 of P minus P prime, like we did before. That's the same thing as we did before. And you take B of P with B dagger of P prime equals the same thing. And then this implies that the commutation rules work. Okay, and I guess I don't know. It's yeah, it's not. I don't have it actually worked out here, but it's just a bunch of the same type of algebras we did before. You know, you've got d0 pi being d0 phi star, so it involves a daggers and b's, and you just do these commutation rules and they all work out. And factors of 2 have been cleverly worked out. And even more so, if I take the Hamiltonian as the integral d3x of this Hamiltonian density that I wrote above, it turns into the integral d3p over 2 pi cubed omega p, a dagger of p, a of p, plus b dagger of p, b of p, plus there's of course an E0. It's 2 times the real result, the real scalar field result that we did before. Okay, so making this choice it looks good. I mean, we start off, we have two real fields, phi1 and phi2. We end up with two types of creation operators, A's and B's, because those are the 2 different fields if you want. There's like 2 different fields. And they each have positive energy and all is well in the world. So you end up with 2 particles with positive energy. Okay, we're postpone a little bit of interpretation. Let's see if I can, actually I'm going to have to rush through it. I'll rush, then I'll review next time. But I don't want to miss this punchline. Okay, the next piece of the interpretation comes actually when you realize that there's actually a conserved current. Okay, and okay, the current, you know, as always, it has 2 pieces. So the conserved current, when I say that, means that d mu j mu equals 0, which is equal to, you know, d rho dt plus del dot j. So just like an electromagnetic current, this thing is conserved. And in fact, up to a factor of the electric charge, it is the electromagnetic current. Okay, I'll write it out for you. J mu, it's phi star derivative phi. So it looks like the momentum acting on derivative. There's a factor of I out in front. And it actually has, then it goes like the following. It goes like minus I derivative on phi star phi. Okay. So this is given the notation phi star derivative left minus right. So there's a double arrow over that guy. And when we do that, it means you take the derivative to the right and minus the derivative to the left. Okay, so it's either acting on phi or phi star. If it acts this way, it's positive. If it acts the other way, it's negative. That's the Hermitian way of doing it. Okay, I don't want to spend time on this thing. If you I guess it's worth checking. I guess we can't get too far without doing the check. I take d mu j mu is, so I take another derivative on that. Okay, well, then I can do a few things. I get d mu phi star d mu phi. So acting on that first piece, there's two terms. It's plus phi star box phi. Right, so that's the derivative acting on the first term. And on the second term, it's minus box phi star phi minus d mu phi star d mu phi. Okay, those are the terms. The first and last cancel each other. The equations of motion turn that into m squared phi star phi. Turn that into m squared phi star phi. So this thing vanishes. Okay. So by demonstration, this thing is conserved. Now, we could later on know that there should be a conserved current, but all right. How much can I do? So, like in E&M, there has to be then a conserved charge. Okay, Q is the integral d3 x of the time component. This is rho. Okay. Okay. If I take dq dt, the integral d3x d0 dt j0. That's the integral d3x minus del dot j by the conservation equation. And that's then minus the integral dA dot j if I integrate by parts. It's a total derivative, so I integrate that. And that goes to 0 if the surface is at infinity. Okay. So the proof I just did there, I whipped through it. I couldn't impress for time. Is just the same proof as conservation of charge in E&M. Just J is the electromagnetic current there. Okay, in this case it's also true. And then if we calculate Q, okay, Q turns out to be the following. So we just plug in. It's the same old calculation. It's the integral d3 p over 2 pi cubed. It ends up being a dagger of p, a of p, minus b dagger of p, b of p. Okay. There's a minus sign there. And the punchline is the physics interpretation, which I'll have to come back and review for you, but let's just do it. There's two sets of states. Okay. We can define, let's call it phi of p, which is a dagger of p on 0, and let's call phi bar of p is b dagger of p on the empty state. then we find that both these have positive energies. H on phi of p is omega p phi of p. H on this is what I call phi bar of p is omega p phi of p. But they carry, whatever this charge is, they carry opposites on it. Q on phi of p is +1, and Q on phi bar of p is -1. Okay. So they carry opposite charges in some sense. And if I just add an overall factor of E, this is in fact the electric charge. Okay, and the interpretation is that these are antiparticles of each other. You know, it's conventional to call A the particle and B the antiparticle, but you could have reversed it in the names. So a real field like this comes particle and antiparticle. I mean, a complex field like this comes particle and antiparticle. With both with positive energies, but with the opposite portions of some charge. Okay? It's the particle charge. You know, one's got particle number +1, the other's got particle number -1. And that's how you differentiate. Sorry for running over. Sorry for rushing at the end there. I'll come back. I'll review that a bit. And we'll go there to non-relativistic physics for a while, and do photons. And probably don't get to Dirac fields next time. Okay?